Hello everyone, I'm Fu Zexin, a graduate student from RIOS Lab under the guidance of Professor Tan. My research focuses on coherent cache and CPU design. Today my topic is coherent cache on PicoRio. As a start, let's take a look at the overview hierarchy of PicoRio memory. PicoRio is equipped with private L1 instruction cache and data cache, along with unified L2 cache. The L1 data cache is hardware cache coherent. The coherency is maintained by a Snoop-based coherent mechanism, especially the Snoop Control Unit (SCU), which logically lies between L1 cache and L2 cache. The Snoop Control Unit conducts all the Snoop operations, fetch the Snoop acknowledge message from each target L1 cache, and return the Snoop result to the L2 controller. Today, our topic is mainly about the design of coherent L1 data cache, especially the cache coherent communication mechanism, split transaction with pipeline cache controller, and our verification methodology. As for the cache coherent communication mechanism, we use TEL-link, which features for its 5 logic independent channels. In the design of TEL-link, channel A and channel D are used for host like L1 cache controller to send request and receive response messages to and from its L2 cache. Channel B and channel C are used for transmitting Snoop messages to and from between L1 cache and Snoop control unit. Finally, the channel E transmits final acknowledge for serialization. And the priority of these channels is descending order from E to A, which help us get rid of potential deadlock. It has several reasons that we choose TEL-link as the logical communication channel scheme. Firstly, it's the clean abstraction. As 5 logically independent channels, with each has its own message spread direction and function, it is easy for designer to implement the protocol on it. Secondly, this scheme provides infrastructure of communication, which is independent from specific protocol. Therefore, we can implement different coherent protocols like MSI, MESI, MOESI, and so on, without changing the topology of overall system. Thirdly, as the 5 channels are assigned to have different priority level, TEL-link is equipped itself with deadlock-free mechanism. With the above features, we found that TEL-link is helpful for the implementation of split transaction, as it split request and response message into different channels, and has a dedicated channel for serialization. We prefer to break atomic transaction into split transaction for more concurrency and therefore better memory access performance. Basically, we split the whole transaction into response and request transaction in order to improve channel utilization and throughput. To support split transaction and more concurrency, more hardware components are dedicated, like store queue in low store unit, in-flight table in L1 data cache, and pipeline L2 cache controller in L2 cache. As for the store queue, it holds store requests from core and issues them to L1 data cache. During the store transaction in flight, subsequent load requests can check the store queue for quick forward data. Like the store queue, In-flight table holds the memory transactions issued to the next level cache and wait for their response. The number of table entry is the number of the transaction it can hold in flight. As the transaction has been selected, L2 cache controller should be pipelined to handle more load and store transactions. As you can see in the graph, the controller has been divided into 3 parts, according to its interaction with different tail link channels, which are fetch and snoop stage, memory access stage, and the ground message sending stage. By pipelining, we can exploit more concurrency and thus better performance from L2 cache, and it matches our split transaction scheme fairly well. Also, we are making our plan for verification. Initially, we make functional model, formal verification model, and RTL model separately. It is a common method, however, it has a major drawback. As we have to implement the same description separately into 3 models, it is a great penalty. What worse is that it is hard for us to prove that these 3 models are equivalent. So, it is meaningful to build a tool which is able to output above 3 models from the same basic input file. Thus, we can save time and effort, and we can be more confident with the equivalence of our models used for the different kinds of verification. We plan to output the C++ functional model and the formal verification model from the same input file as our step 1 goal. We make this plan because these 2 are verification models which do not have to include many hardware details. So our input file and building tool can be high-level abstract to some extent. For our final goal, we hope to build a tool which can also output RTL model which describes rich detail of our hardware implementation. For your information, rich detail of our formal verification methodology is contained by Jerry Liu's talk, part of the presentation of City University of Hong Kong students. If you are interested in our formal verification, that talk is for you. This is all my talk today. Thanks for your attention.